Good afternoon, everyone. It's a great honor for me to introduce today's colloquium speaker, Dr. Bernard Kres. And Bernard has made many significant contributions and wear many hats in the past as an engineer, as a researcher, as an associate professor, instructor, inventor, and author, and many. And he has made contributions from the instrumental contributions in many areas, especially optical system for consumer electronics. And he's currently the partner optical architect with the Microsoft Hololens. He previously worked as the principal optical architect at Google X. You probably have heard of the Google Glass project, and he's instrumental to that one. And you can see, and he published many papers and books, and his most recent one is the field guide that just came out a month ago, right?
It's not a field guide, it's a monograph.
So, monograph, okay. Yeah. And on optical architectures for virtual reality, augmented reality displays. And today he's going to talk to us about optical challenges that pave the way for the future computing platforms, and he has lots to say about why it's challenging and why this opens up opportunities for you guys as a students. And without further ado, I'll give the floor to you.
Oh, thank you. Thank you. Thank you, Hong, and thank you for inviting me. Also, thank you, John. He's not here, but he's going to come a little later. It's an honor and a privilege to be here. I heard so much about this Optical Science Center since 3 decades now. This is my first time here, and I'm so privileged to be here among you. I'm also very humbled to be here among the most amazing students in optics on this planet, and I can say it. You know, it's amazing to be here. So I'll talk a little bit about optics this afternoon, but it's the end of the afternoon, so I know that you're a little tired, and it's going to be very enjoyable because there are a lot of videos, there's some sounds, and there's some interesting, not many equations and much text on my slides. So I'm not going to talk only about HoloLens. I'm also going to talk about other headsets that I had the privilege to test out, but I'm going to talk a lot about HoloLens. We have a lot of students from this college in Redmond, in the Silicon Valley. So I'm based in the Silicon Valley. Back at Google, I had a lot of colleagues that also came from this amazing school. So of course, half of them come from Arizona, the other half come from Rochester, you know. And what I said, and I'm going to tell you this also, it's at Google, 5 years at Google, 5 years at Microsoft. They don't mix. When they go to the cafeteria, you have the table with the Arizona people and the table with the Rochester people, and I always go there. I'm from France, so I can actually be the mediator and say, please, this is just like a Catholicism, Protestantism, there's like 2 different religions, and it's a little better when they mix, and I'm trying to do this at Google, and I'm trying to do this at Microsoft. So I'm acting a little bit as the mixer and the catalyzer there. So just for your information. Okay, so a few words about me. Oh my God! Wow, I'm blue now. I don't know why it's blue, but it's not blue on my screen here. So it must be the projector. So just a few words, but in 1991 I started to work in holography at Worcester Polytechnic Institute on holographic interferometry. Then I went to King's College London to work on diffractive optics. I went to UC San Diego, working on the Dr. Sing Lee on diffractive optics for mainly applications in optical computing back then. Then I was professor at the University of Strasbourg in France. We took part in this. This was actually amazing. It was a Eureka, a European project, FOTA, flat optical technologies and applications. That's the first time that was actually introduced to the concept of waveguide gratings. Of course, that was not display. Nobody really was interested in display in these days. Everything was optical computing, optical interconnection. That was a wave that, of course, crashed. Everybody, remembers Joe Goodman. Joe Goodman was actually working very intensely in these applications. These are some books that I published in the 90s. Digital diffractive optics. I also worked at Digilens. They made dynamic holographic media, HPDLC, holographic polymer dispersed liquid crystal. They're still around today in the Silicon Valley. Worked at USI Photonics, which was a wafer, a micro-optics wafer fab. Oh, I published something with Bob Fisher. Published a chapter in his bestseller Optical System Design. And then I published this book here at Wiley. This is actually a good one. These guys are not that good. Applied Digital Optics. We actually started a conference series at SPIE, Digital Optical Technologies, in Munich as part of Laser Europe. Every odd year in Munich. So I invite you to participate there. A few other companies that I worked in. There's a field guide that I published a few years ago, Digital Micro-Optics. Another chapter in the book, Wearable Computers and Augmented Reality. And there's another one, Micro and Nanophotonic Technologies. Then I started to work at Google in 2010 on the Google Glass project, and then of course at Microsoft on the HoloLens project. Oh yeah, and who was at Photonics West? Yeah, a few people. Did you also have the pleasure to go to SPIE AR VR MR on Moscone West? Yep, a few. So we had this first conference, which graduated from Photonics West. It's now a self-standing conference, and we're going to have this again next year in early February. So I invite you to come all and to attend this conference, this new conference, which is now going to be running every single year in parallel with Photonics West, also in the Moscone Center. So similarly to John, I also like to collect vintage optical systems in my garage, and I think everybody knows, the telescope and microscope collection. For me, it's a little different. This is a mask aligner from the 80s, which I have in my garage, and this is a Wyco. This is a Wyco 3D topo, which I have in my garage also. It actually runs on a HP workstation, which has a 5-inch floppy disk here, 3-inch floppy disk, sorry, an Atari joystick here. But it actually works. It's a monocolor, so it measures lambda over 4. But it works very well. I have it in my garage also. So my wife hopes this is just a temporary medical condition I have, and that I will get rid of all this pretty soon. And I don't think it's going to happen. Again, sorry about the color. This is red on my computer screen, but it appears blue on the projector. So I don't know what happened, but let's see. So after half a century of 2D display technologies, which have very limited experience, such as the TV, the computer screen, the laptop, the tablet, the cell phone, whatever, these are all 2D display technologies. Even though you can implement a light field or a lenticular 3D display, it is still a 2D limited experience. Finally, we go to near-to-eye immersive display, about an inch or less from your eye, and field of views that are ranging from 40 degrees to 220 degrees, whereas even with the largest LCD screen, you're only at about LCD TV, you're only about 40 degrees or so. Yeah, so I talked about this. This is the conference that we had last week, 2 weeks ago. So again, I invite you to come next week. So what is mixed reality? Well, of course, it's a blending of the real world with the virtual world, but there are a few other names, such as diminished reality, where you actually take things away from reality rather than adding things to reality. For example, you're driving down Las Vegas and you don't want to see anything related to firearms. Your headset can actually detect it and just blank it out, or replace it with advertisement for candies, for example, which is then a diminished reality superimposed with augmented reality. Then contextual display. This is typically smart glasses. Smart glasses are not augmented reality display. They're monocular. They're a small field of view. They don't have a lot of sensors. So we talk about contextual display. Typically, Google Glass is a contextual display, head-mounted display. It adds information on. The information is actually floating in front of you, or can be somehow with 3 degrees of freedom. IMU can be stick on a building or on something else, but it's really it's basically just text. Then of course you have augmented reality, which is digital information that augments your reality. Then you have merged reality. Merged reality is not so much used anymore. It was a term that was used by Intel some years ago to refer to mixed reality through video pass-through AR. So it's opaque, but you have the video pass-through. But it's not so much used anymore. People use more video pass-through virtual reality. And then you have something else. Yeah, that actually struck me at CES, a few months ago, a couple of months ago, the concept of parallel realities. It's not augmented reality, it's not virtual reality, it's not mixed reality, it's parallel reality. So what is parallel reality? There's no headset anymore. Okay, so since 10 years we have this device here, and everybody has it, but of course it's gonna go away. And 2018 saw the first drop in the sales of smartphones. 2018. So Apple is really interested in finding the next big thing. What is the next big thing? Maybe a wearable, maybe not. But if it's a wearable, we might have it for another decade or maybe a decade and a half. What's after that? I don't think they're going to be wearables. I don't think in 15 years anybody wants to wear a piece of electronic, either on the glasses or anywhere else on the body. We will actually be embedded in IoTs, which actually recognize you. So this is a table. The first thing to understand is 300 years ago, 400 years ago, what did we have? We had tables, we had chairs, we had walls, and we had windows. 400 years later, well, we have other stuff, but that's not going to, it's just 10 years, it's just a blip on the radar, We're still going to have tables, we're still going to have chairs, we're still going to have walls, and we're still going to have windows. Now imagine all these sensors and these stealth displays integrated in these 4 things that we will still have in 400 years. We will definitely not have this, we'll definitely not have a head-mounted display, but we'll definitely have chairs, tables, walls, and windows. And I'm going to talk a little bit about how displays and sensors can be integrated in something like this at the end of the talk. So just to open your horizon, just don't think about head-mounted display as something. This is really what's going to impact us in the next in the future. You're relatively young for most of you, and in the next 30 or 50, 40 years. I don't think head-mounted display will be that big thing. It will be also a blimp on the radar, like this guy was a blimp on the radar. So I think IoT devices that incorporate sensors that will sense you and that will be very secure and that will be able to provide you information without anybody else seeing that information will be prevalent without the use of a head-mounted display. Okay, so today, in 2019, we have about 1 million jobs enhanced globally by VR and AR. Now that number will jump in 2030 to 23 million jobs enhanced by VR and AR. These are jobs. These are enterprise applications. So what about consumer? I don't know. I have no idea what the consumer would do with an AR glass or a smart glass. At Google, we thought that a consumer would embrace smart glasses. Well, we were completely wrong. And it was a big failure. V2, smart glass, was an enterprise device. V3 is an enterprise device. Hololens V1, 2015, was a shot in the dark. We had no idea if there was a consumer market or an enterprise market. So we said, okay, let's target it partly for consumer, partly for enterprise. What was the result? No feedback whatever from consumer, but larger feedback than we imagined from enterprise. What happened last year? We introduced H2 as a pure enterprise augmented reality, mixed reality device. Not for consumer. Apple, a lot of this school provides a lot of very good engineers for Apple, and they're all working on very interesting hardware. And I know for a fact that they have hardware ready, and not in a hurry to push it out, because Apple is a consumer-oriented company. They don't see a market. So there's no reason why to push it out. So you see, we're in sort of a period where there's an immense traction for enterprise, and also from defense, as you will see later, but no traction yet from consumer, because the use case is not there. There's no use case today. You can read your mail, you can get a time, you can get directions. These are not use cases. You can do this very well with your smartphone. There should be a revolutionary use case, and we don't have this yet. But the use cases are here and are completely revolutionary for enterprise. So, yeah, the colors are just completely. I don't know what happened here. This is blue. This is the Microsoft blue.
Was it supposed to be blue, not red?
So, and there's a problem here because I have the sound coming out from my computer and not from these devices here. So they might not be on. So, yeah, so the HDMI carries sound, so it should be. So I might just use this one here. So.
Mixed reality breaks down the barriers between physical and virtual realities. Let's see how we can alter realities across people, places, and objects. Here we have a real office, populated with real things. Let's now adjust reality by adding virtual objects to this physical space. Notice how these objects are aware of the real surfaces of the office. Next, let's replace the real person with an avatar. This allows her to be present, even though she's not physically in the room. Now let's adjust the environment itself and make it virtual. Notice how the virtual objects and avatar continue to persist. Finally, let's tie back this entire virtual scene to the original physical room. A subtle boundary can reveal real obstacles, making it safer to walk around this virtual environment. Mixed reality unlocks exciting new experiences that merge the physical and the virtual worlds.
Yeah, that's blue. So as you saw, the definition of mixed reality is first of all scanning your reality, making sure that the device understands your reality as a three-dimensional space in which you can superimpose digital information, which we call holograms, and not holograms, a stereo display, 200 euro stereo display. But the first thing, unlike augmented reality, you scan your surrounding. Now, how do we do this? With a time-of-flight scanner here. And I'm going to talk about this later. So that's a big difference between mixed reality and augmented reality. In mixed reality, you really want to have your pink elephant sitting on the chair, not floating on top of the chair, or being under the chair, but really sitting right on the chair, because the chair has been scanned and your head is tracked, so the display knows exactly where to put the pink elephant. So it looks actually real and sitting on that chair. In an augmented reality display, the pink elephant would be maybe a couple of inches over the chair or in the chair or floating around. That's a big difference between augmented reality and mixed reality. Sample use cases. Yeah, they all look like remote assistance, training and task guidance, collaborative visualization, and contextual data access. And for me, remote assistance is actually the biggest example, and you will see this in a video pretty soon. So I talked about defense also. So Magic Leap was bidding on an Army combat contract in 2018, but actually Microsoft won the contract. It's $500 million. There's 2 more billions coming, so it's like $2.5 billion, which is not a small purchase order. It's not investment, it's a purchase order. It's the largest purchase order ever written in the history of VR, AR, MR mixed. And there's a huge demand from defense. Now, of course, that oh my God, that provoked some problems in Microsoft from employees who said, yeah, we're not going to work for the Army. But the fact is that the Army was the largest client for Microsoft since its beginning, and Microsoft is Microsoft mainly because of Army contracts. So employees are very happy of the stock chart today, and and the fact that Microsoft is what it is. So they actually swallowed it, and and understood that working for the Army is actually a good thing, at least in this country here. So this is what we're doing for the Army. A lot of different sensors. Can't really talk about it, but that's public. And you can have all the information on fedbizops.gov if you're interested in the IVAS, the Integrated Visual Augmentation System, and the specs, and when it's going to be deployed, how many, and so on. So it's all public. It's a public market. FDA approves first. So this is surgery. First Microsoft Hololens augmented reality system for surgical use. That was in 2018. In 2 weeks, March 5th, if you're interested, there's a public workshop at the FDA, the Food and Drug Administration, medical extended reality towards best evaluation practices for virtual and augmented reality in medicine. Hong, I think you're also a part of it, yeah. So, it's going to be a real interesting workshop, the largest one up to now. Last year, we launched HoloLens V2 at Barcelona, Mobile World Congress, the congress that was cancelled this year because of the coronavirus. So, as I said before, V2 is a 100% dedicated enterprise device. We don't want to cater to the consumer market because we know that there is no use case today. So these are some examples, some videos that from our partners that show how they use HoloLens V2 in their companies, and how they improve the efficiency and the productivity of the workers, and how they actually gain a return on investment on on mixed reality.
1420, Brunelleschi, Renaissance architect and master builder. He invented a new way of seeing reality, and that's the illusion of perspective. That perspective representation is now able to be part of our physical reality.
We are out here today at a construction site which is probably one of the most iconic buildings that's being built in the Netherlands. It's a depot for a museum here in the city of Rotterdam. The real need for the digital transformation in our industry is really about avoiding rework at our construction site.
Bentley's work is the Hololens to bring digital models and merge those with physical reality. The digital model is now becoming part of our physical reality. That's the real innovation.
The 2D screen can't convey a problem that's so complicated. You add augmented reality to that, and you can understand what's really happening.
We can see, hey, we're behind, so we can flag the issue and look into the problem and adapt the schedule to get back on track.
So that's where the efficiency comes in. We've compressed the time of understanding of a drawing or a Gantt chart to basically instantaneous understanding. The models that our customers produce are of massive scale and complexity. The only way we can really effectively get that kind of complexity into an experience in the HoloLens is to leverage the cloud. This is where Azure GPU really comes into play. That is what enables us to finally deliver an experience in the field.
Having a schedule and a model integrated together, and then being able to look at it with what's going on a construction site is a huge opportunity. Understanding how things are going to happen, HoloLens is definitely taking us into the future. It is visionary.
So, return on investment by cost avoidance, by speeding up the learning curve for employees, by having a higher productivity, higher yields. That's exactly what it is about. So let me take the HDMI out and in again, because I'm sure we can gain the color. Okay. Is it better?
Yes.
Okay. Well, perfect. Oh, okay. Wow. Okay. This is another one.
Today, industrial companies are facing serious issue around downtime.
No.
Industry report suggests that
No.
a single hour can cost between $1 and $5 million. At PTC, we are helping our industrial customers reduce downtime through Vuforia, mixed reality, and augmented reality solutions. PTC's Vuforia Studio solution allows customers to easily drag and drop and create a mixed reality experience in hours instead of days or weeks. Using PTC's Vuforia Studio, one of our industrial customers, Howden, was able to easily and quickly create a mixed reality experience.
Howden is an original equipment manufacturer. Our products can be found in virtually every air and gas application. If this equipment ever goes offline, it costs a lot of money.
Compressor is a critical equipment within the wastewater plant. Plant operators are not typically expert of compressors.
Our customers are looking for us for solutions to empower them and how to best service their equipment.
Today, Howden is pulling ThingWorx data that's operating on an Azure IoT cloud, and it's overlaying that information in context through mixed reality.
We're overlaying the digital twin data on the physical product to show our customers the operating condition and the performance of the equipment.
Literally at their fingertip, we can provide 160 years of compressor knowledge.
Using Microsoft HoloLens, that customer experience is truly immersive, and you get to understand a lot more, and it's just a new way of looking at your equipment that you've never had before.
With the PTC Vuforia solution and the Microsoft HoloLens together, I think we can really provide a transformative experience for our customers in the industrial market.
Okay, and then the last one, my favorite one, is in healthcare and surgical image-guided surgery. This is by Philips.
In the image-guided therapy business of Philips, one patient every single second somewhere on Earth is treated with one of our products. So that's 28 million patients a year can be treated because of the work that we do here. That was the big reason I came to Philips. Image-guided therapy is modern-day surgery without the incision. We're navigating tiny instruments through the body through incisions no larger than a pencil point. We're relying solely on X-ray images or medical imagery to guide us. So that means we are always looking at a screen of data.
With HoloLens,
We can take it to the next level. We are a leader in image-guided therapy, and with Azurion we created an industry-leading platform that customers really love. What's really cool about it is we've leveraged novel touchscreen technology to create a very powerful working spot for the physician. Our ultimate goal is to help doctors do procedures better, to help them innovate the procedure. With Hololens, we can create a completely different experience, a working domain which is really tailored around the needs of the physician.
For complex procedures, physicians need to go from one screen to the other really rapidly. We can now get these screens to come in just by voice recognition, by eye tracking.
This is all about efficiency.
If patients are being treated and the procedure can be shortened, it's very beneficial for the patient.
At Philips, we strongly believe that technology is not the goal, technology should be the enabler. What we want is that the physician can just concentrate on the procedure and the patient, get them home faster and healthier. This partnership between Philips and Microsoft can have our users experience something completely new, something almost mind-blowing, something that they didn't think was possible, and help them improve care. That's a great thing. That's a complete game changer.
Okay. So, you saw 3 different applications. Let's go more into the hardware, and that's what we are mostly excited here, and especially optical hardware. So, what are the key pillars for the adoption of mixed reality systems? Well, first is comfort, and then immersion. Now, comfort comes in 4 declinations. First, you have the wearable comfort, you have vestibular comfort, visual comfort, and eventually social comfort. So comfort comes in different varieties. Of course, the device has to be untethered. There's no cables. That doesn't mean that it cannot be tethered to the cloud. It has to be tethered to the cloud because somebody needs to make money, and nobody makes money by selling hardware. Hopefully, Microsoft will have a good business in providing mixed reality cloud services on every single headset on the planet. And today we need to design and produce these headsets because nobody else is doing it at our place, but really don't want to be a hardware company. The device has to provide wide IPD coverage and prescription correction, high angular resolution, no screen door effect, small size, small weight, center of gravity close to the center of gravity of your head, versus accommodation, conflict mitigation, high brightness, high contrast, no ghosts, no pupil swim. Thermal management. Thermal management is one of the most critical one. Remember that in the case of HoloLens, you have 2 2K screens on. You have a PC, and you have an Xbox, and you have a Kinect. And everything is sitting on your head, plus the battery. So you don't want your head to start to cook, So you need really to, the most difficult thing, I wouldn't say it's optics, it's just thermal management today, and passive thermal management. You cannot have a blower, on your head, and this is really, really important today. I'll show you a little bit what we're doing in this field. Immersion, of course, field of view, but field of view is a 3-dimensional concept. You need to have arm's length display interaction capability. Also world-locked spatial audio, which is a big part of the immersion. Foveated and peripheral display, hard edge occlusion, active dimming, soft edge occlusion, high dynamic range, and accurate gesture sensing. And of course, motion to photon latency, that's maybe that has to be below 10 milliseconds. Now there are 2 latencies. In video see-through, video pass-through, the video feed has to have a latency of less than 2 milliseconds. But the added digital information on top of your reality can have a latency of 10 milliseconds. Right now, H2 is about 9 milliseconds. Any video see-through has to have a 2 millisecond lag. Maybe that's why Intel was not successful with the Project Alloy a few years ago, because that 2 millisecond range was not accessible. Today it is accessible, and I'll show you an example. And of course 3D display world locking, and a lot of them are only implementable thanks to fast, accurate eye tracking, and we'll talk about this later. So everything, and this is also Honghua's credo, everything has to be human-centric optical design, because you design not only not for a camera, but for the human visual system. So the first mixed reality pillar is immersion. Retinal resolution, high dynamic range, and field of view. You have to match the human eye vision. And this, this is has also a name, optical foveation. So the human eye is only high resolution in the center, is your fovea and macula. Therefore, so you can actually move your eye around plus minus, I would say plus minus 15 degrees or so without having any eye strain. So here's a graph showing the human visual system, how it's actually limited. You have your fovea, it's about 3 degrees, text recognition about 20 degrees, symbol recognition about 40 degrees, and color discrimination about 60 degrees. And after that, you don't need, you cannot resolve high angular resolution anymore, you cannot resolve color, but there's a lot of things that you really resolve very well in the periphery. For example, jitter. You resolve jitter much better in the periphery than in the center, than in your fovea. Because we're wired this way. When we're sleeping in caves, a few 100,000 years ago, had to make sure that there was no snake or no spider, and this is the jitter, on the side. When it's in front of you, it's usually too late, So that's why it's very, very important to detect it on the side. But then again, you don't need color and you don't need high resolution. So this is a human visual system, left and right. Here you have the fovea and the parafovea. So there's a fixed foveated region, which is about 40 to 50 degrees. Full angle. This is the region over which you can actually rotate your eyes and still be able to gaze without having to rotate your head. So you can do a little test. You rotate your eyes by 15 degrees and you can actually stare at somebody. But then you can mechanically rotate your eyes plus minus 30 or even 40 degrees, but then you have eye strain. What do? You rotate your head. And you're not able to gaze at something and really get the high resolution out. So this graph is interesting. This is the angular resolution in arc minutes as a function of the viewing angle from the center. So you don't rotate your eyes. So right in the center, you can have a 1 arc minute, even lower than 1 arc minute. Then when you're at 5 degrees, it's about 3 arc minutes, 10 degrees 4, and then 30 degrees, you're around 12 to 15 arc minutes resolution. So, concept of optical foveation. Well, optical foveation is very different from foveated rendering. And let's see the differences. So here I have this is really good because it's all grayscale, so there's no color coding problems here. So light gray is a GPU rendering. Medium gray is a number of pixels required, physical pixels required in your display, and of course black is the perceived resolution by the human eye. So when you have a low resolution display, well of course GPU and number of pixels low, but also perceived resolution low. You put everything high resolution. The problem is GPU rendering and number of pixels required go up. You can have optical foveation, which is always in the center. Then you have GPU rendering low, number of pixels still high, because this is foveated rendering. So you have a high number of pixels everywhere, but you just render in the center. Now sometimes you're not interested in the center, but you're interested, for example, here, the Mona Lisa, you want to look at the face. Then you need gaze contingent foveated rendering. But if you have the chance to have 2 displays instead of one display being high resolution, which is in the center, and a low resolution display for the periphery, well, you can actually reduce the number of pixels required and reduce the GPU rendering. But of course, the perceived resolution is only high in the center. And then of course the Cadillac would be gaze contingent optical foveation on 2 displays. One display would be high resolution, steerable. Wherever you look at, the high resolution display follows your eye, and the low resolution display, high field of view, is static, just stays there. So that's really what we need for the future. Not for the future, because a lot of companies are actually providing this today as prototypes. Also, this is interesting, the combination of unaltered see-through field of view and display field of view creates the mixed reality immersion experience. So a few people think that the ratio between the digital display and the see-through is important and will allow you to have the perception of a larger field of view. This would be Magic Leap, where they close the see-through field of view specifically. Now, we don't think that's true, so we opened the see-through field of view in HoloLens. We just have it closed here because we have all our sensors that I'm going to show you a little later. Also, what is interesting is for an optical engineer, the field of view can be measured. It's 50 or it's 50.5. There's a difference. Now, so we did this test at Microsoft. We used software engineers. We have a lot of them. We don't have a lot of optical engineers, a lot of software engineers, and we said, okay, this is a display at. We didn't tell them the field of view. We just asked them which field of view from head-mounted display 1 to head-mounted display 2 seems the largest. So the first field of view was a 40-degree field of view. The second headset field of view was 50. But the image, the MTF, and the contrast of the 40-degree field of view was better than the MTF and the contrast of the 50-degree field of view. Most of the software engineers said the first device has a larger field of view. So 40 is larger than 50. It's perceived larger because the image is clearer, is crisper. It's all subjective. For an optical engineer, 40 is smaller than 50. For a perceptual engineer in mixed reality, it's not so clear. 40 can actually be bigger than 50. As experience, it's all experienced by the user. So let's look a little bit at display engine technologies. Is HDR, high dynamic range, possible for AR? Now there's a lot of panel displays today. This is the low temperature polysilicon LCD or in-phase switching LCD. For VR, then you have the active matrix OLED display. Then you have all the micro displays, which are usually used for augmented reality. You have the high temperature polysilicon LCD, which is a copying, for example, a copying display, which requires a backlight. Then you have the LCOS display, which is a reflective display, which also requires illumination. Then you have the DLP, which also requires illumination. I've seen a lot today. The DLP MEMS, and these all require an illumination engine. Now, an illumination engine, what we call the display engine, is in a head-mounted display, is the optical system that creates the image. And then you have the optical combiner that combines this image with your reality. So there's two systems. So we talk about the optical light engine, the display engine. Okay. Typically, the size of the display engine, 2/3 is the illumination, 1/3 is the image generation and the pupil generation. So if you can cut this 2/3 by using emissive displays, such as a micro OLED or micro inorganic LED display, well, of course, these are emissive display, you cut dramatically the size of the display. Now, why don't we do this today with HoloLens? Because a micro OLED display has a maximum of 1,000 nits or so, maybe 1,500 nits brightness today. If you crank up the brightness, you reduce the lifetime of the organic LED display. But with a micro ILED, inorganic LED, well, you can have 100,000, 500,000, or even close to 1 million nits without destroying the device. So everybody is actually very excited about this. We had a panel session at the show 2 weeks ago, and we invited most of the companies that are involved in micro ILED displays, and we asked them the question, when is it going to be ready? And depending on who you talked to, you know, if you're talking to the CEOs of the company, they were talking about 2 to 3 years. When you're talking about, there was actually a technical journalist also there. He said 1 year. But the actual companies said 2 to 3 years. So these are technologies that will come up in 2 to 3 years. All the rest is available today, you know, but this is actually the most interesting for AR. Not for VR, because you don't need the brightness for VR. You know, a few hundred nits is okay. But in AR, you know, because you lose so much light when you use your combiner, especially a waveguide combiner, it's typically only in the single digits efficiency. You need a very bright display. Here are some of the displays. Here are some of the brightness of the displays. Of course, micro OLED would be the smallest, you know, then high temperature polysilicon with a backlight LCD. And then, of course, you go to LBS. LBS is laser beam scanner. It's what we have in V2. And then free space illumination of DLP. That would be the brightest display that you can actually have. It's free space LCOS is what we use in V1. You know, of course, it's polarization sensitive, but DLP free space can actually be much brighter. Now, of course, you need more power to drive a DLP than to drive an LCOS. So that's why, you know, people still prefer to use LCOS than DLP in a wearable device, because you need more power to drive the DLP today. And of course, the micro ILEDs are here, so go from 500,000 nits to much more. Scanning, so I talked about LBS, laser beam scanner, not only as a dual MEMS, but single MEMS, but also as a piezo fiber scanner, or a surface acoustic waveguide scanner. There are many different scanners available today. If you want more resolution, for example, you have a DLP and you can't really get more resolution because you can't get TI to fabricate a DLP with enough resolution, then you can do wobulation. Now, in the old days, you use wobulation with a spinning prism. Wobulation means you move a little bit the display so you can create pixels in between pixels, but you have to refresh at twice the rate. Okay, so that's called wobulation. It was invented by TI in the 80s. So today you can do a solid state wobulation, or you can even switch on different LEDs in your illumination system, and you can have solid state wobulation. You know, that's also what Magic Leap does, but they don't use it for wobulation, they use it for pupil steering. So this is an interesting graph. I'm going to spend some time here. These are the various laser ILED scanning display architectures today. So, you know, if you use a 10-year-old microvision laser scanner, you have a 2D MEMS scanner and one laser, and then you scan your image, okay? So everybody knows this. You can actually use 2 scanners and 1 laser, and this is what Bosch is doing in their latest smart glasses. Bosch knows 1 or 2 things about scanners because they actually invented this for in the 80s for airbag sensors, not display. This is what we do in a HoloLens V2. We have 2 lasers per color and 2 1D scanners. Why 2 1D scanners instead of 1 2D scanner? Because they're more reliable and they can actually scan over a larger angle. One is a fast scanner, typically a piezo scanner, and the other one is a slow scanner, typically a electromagnetic scanner, MEMS scanner. Then you can scan 1D arrays of ILED pixels, such as, you know, what Nintendo did in 1995 in the Virtual Boy. So you have one. Actually, they use a galvanometric scanner, not a MEMS scanner, because they didn't have MEMS scanners at that time. Galvanometric scanner that scanned a 1D array of LED pixels in the other direction to make a VR display. Because at that time, well, engineers didn't have access to this because that didn't exist. So they had to paint the image with some other means than, you know, a cell phone display. Today, sorry to say, but today you know, we're creatures of habit, and everybody has this in their pocket, and nobody really thinks about anything else but this to create a display in a VR system. 20 years back, engineers had to scratch their heads a little bit, and this is actually a very nice architecture, which I think is going to come back. This is a 2D scanner with 2D scanner which actually does wobulation. So this is typically a wobulation, a field of view, and in this field of view, you wobulate your display with the 2D scanner, mirror scanner, to create more pixels in this field of view. You can actually create a larger field of view with a mirror that moves about the field of view to create a larger field of view with the same resolution. But I think this is the most interesting. This is actually a switch in between. You have a small array, let's say your LCOS array, and then you move it around a fraction of the field of view so that you actually have optical foveation. So you have in your angular space more pixels in the center than on the periphery, with a micro display that has only one resolution. Okay, so that's a very interesting scanning device. Popular light engine, LCOS and DLP. This is a LCOS light engine. This is Hololens 1. This is Magic Leap, and this is a DLP, typical DLP light engine. This is a Hololens H1 light engine. Here you have the exit pupil, which is the entrance pupil of the waveguide here. This is the LCOS plane. I don't show the illumination system. So it's the PBS. Obviously the illumination comes from here. Then you have bird bath beam cube here, and you create the input pupil. So you have about, let's say, 200,000 nits here. You have about 1 million nits here, close to 1 million nits here, as the entrance pupil of the waveguide. And then when you come out, this amazing waveguide is actually a nits slasher, and provides only 500 nits at the eye here, with close to 1 million nits at the entrance pupil here. So you see how efficient the waveguide combiner is. This is again V1, this is V2. In V2 we're actually using a laser scanner light engine and a similar waveguide grating combiner. We're going to see this later. This is a video that introduces H2. These are the sensors. Line of flight sensor. This is the fast scanner, the piezo scanner. These are the relay lenses, which are reflective, and they bounce off a slow scanner, electromagnetic scanner. The external skin is it's very weird to see this. This is an overview of the laser display engine. So you have RGB coming in here. You have actually two lasers per color. They're slightly separated, so you paint your image with two lasers per color. You combine them. You have the piezo mirror here, which is the fast mirror, in the tens of kilohertz, and then reflective lens relay. And then hybrid achromat here. Transmissive, and this is the slow scanner here. So this is the scanner that then paints the image in the other direction. which actually produces the input pupil here for the waveguide. So this is the output pupil here of the display engine, which is the input pupil of the waveguide that then replicates this pupil and provides it to the viewer. This is how it works in the K-vector space. So you have, this is actually red on my slide. You have a input field of view coming in here. So DOE1, diffractive optical element number 1, traps the field in TIR and then pushes it on one side. But as you can see, the incoming field of view is too large. This is the TIR condition here. And this is another condition for pupil replication here. So part of the field of view is actually lost. See? That field of view is smaller than this one. Now what do? We also propagate it the other way. We also lose part of the field of view, but we lose the other part of the field of view. And when you recombine these two field of views with diffractive optical element 3, which is an extraction grating, you recombine both field of views to create the large field of view, which is impractical to travel by TIR in one direction, so we have it to travel in both directions. We call this a butterfly. We also have two plates, two waveguide plates to propagate 3 colors. So the first plate propagates the entire red. So of course a diffractive element is highly dispersive. So it diffracts. Actually, it's the colors are actually. So this is actually green, and this is red. So John, there's a problem with the projector. It doesn't. It projects different colors. So I have to be careful when I show diffracted colors here. So this is green on my screen, and this is red. So the entire field of view of green is actually trapped by TIR here. But the right part of the, sorry, this is green. The right part of the red is lost. This is blue, and the left part, sorry, this is green. Sorry. This is blue. This is blue. I can show you. I can show you the color on my screen. You have to replace this projector. It's really, really, really painful to. This is the first time actually that this happens. It's really, really not easy to explain this when the colors are completely changed by the projector. This is green. So red is green. And green is red. Okay? So the green is diffracted. The entire field of view of green is diffracted and can be trapped by the TIR condition. The right part of the red is lost. Here, the entire green is just forget what I said. This is actually blue. So red is blue, and green is green. Okay.
Red is blue.
So the projector changes blue into red and red into blue. Okay. So the entire field of view of blue is diffracted and trapped by TIR. The green, the right part of the green is lost because it's diffracted at a larger angle. This blue is actually red. So the red is all trapped by TIR in the guide. The left part of the green is lost. Now if you use 2 guides, you have the left part of the green and the right part of the green that is then recombined. So this is blue and this is red. Did you get it? Yeah. That is actually really, really interesting. When it doesn't change the color of green, but it flips the color of blue and red. Crazy. And then, of course, the holy grail is to go to a single guide, where you have RGB propagating in a single guide. But in order to do this, you need a higher index. You need an index of 1.9, or maybe even an index of 2.0. Right now, in this case, we have an index of 1.8. So wearable comfort. Wearable comfort is very important. It has to fit every single head. And we didn't have access to a good library of heads, so we scanned our own heads. We also have a very nice fit on HoloLens 2. So the important thing here is that the computer is here, the battery is here, the holographic processing unit is here, all the sensors are here, and the Waveguide combiner is here. The center of gravity of this device is actually right here, right at the position of the center of gravity of your own skull. So that's why the weight of H2 is about the weight of H1. But the comfort of using H2 is much greater just because of the position of the center of gravity. So this is really important. Size and weight is one thing. Center of gravity can just change the entire dynamics. And the position of the center of gravity is really important. The weight of the material is also very important. So we use carbon fiber for the front enclosure. Really passes the drop test. I'm not talking about the MEMS. The MEMS are going to freak out. But the enclosure has to be really sturdy and very light. I talked about thermal management. When you have Surface 4, when you have Xbox, and when you have a Kinect and two 2K monitors all on your head, and you don't want it to heat up, you need very, very exquisite passive thermal dissipation, and we use a vapor chamber for this. It's not new, but it's the first time that is implemented in a headset. We also customize the device for helmets in order to improve the wearable comfort for workers in the field, as you saw with Trimble on the video before. So improving wearable comfort in VR headsets. So this is the timeline for VR headsets. We're about here with the untethered, inside out, 6 degrees of freedom VR headsets, but that's not what I want to show, is how to reduce the size and the weight of the VR lens. Well, this is the regular VR lens. You can make a Fresnel. You have all the problems with Fresnel lenses. Then you can have a lens, the center of which is pure refractive, and then you go to Fresnel. This allows you to have a better MTF in the center and a smaller lens, thinner lens, and you will have the Fresnel artifacts on the side, on the field of view. Then, of course, you can go to dual Fresnel shells, such as Wearality. This is actually a very lightweight lens for very large field of view, but the Fresnel artifacts are actually pretty severe in this one. Reducing the lens to display distance. So here we're not trying to reduce the size of the lens. We're trying to reduce the distance between the display and the lens so that we push the center of gravity closer to the center of gravity of your head. So this is the traditional way. You can use a Pancake lens. Pancake lens is a polarization lens where the lens is actually acting in reflection. So one polarization doesn't see that lens, and then you have a polarization reflector here, and turns the polarization, your P now, and you see that lens, which is basically a bird bath lens, which then collimates the field. This is a 3M lens. This is a traditional Pancake lens. And then you have the multipath lenses, which are basically two lenses together with two displays that then merge the two displays at the eye relief. So at the eye relief, you actually see one image, although if you go further away, you see two images that are actually overlapping. So you can also do optical foveation. You have two displays with fixed resolutions, and when you combine them, in the center, you have a higher resolution than on the side with two displays that have single resolution, multipath lenses. And then, of course, microlens-based display. So this is the continuum. You go from single lens to catadioptric lenses, to compound lenses, to fractional display lenses, and then light field rendered scenes here. Pancake lenses are not new. This is 1969. They're used more and more today. Pancake lenses are polarization lenses, so you can't have any birefringence in the lens. So people used to use glass. Glass is heavy. Not used in VR, because it's way too heavy. So low birefringent plastic, it's difficult to get. You can't really injection mold plastic and hope to get low birefringence. You rather cast it, and then you have thermal annealing. So today people know how to make low birefringent plastics. 3M actually did it, and a few other companies did it. So you will see more and more of these pancake lenses now as plastic lenses. Video see-through VR products. Again, there's this 2 millisecond lag, which makes video see-through VR practical. So they don't give you a visual discomfort. 2 milliseconds was impractical even a year ago. Today, I've seen multiple companies that can actually provide a 2 millisecond lag. So these are some of the lenses that I talked about. So the VR systems of the past, like the Oculus CV1 or the Oculus Rift S even, which is from the past, but it's only a year old. The HTC Vives, the clunky VR systems, you will not see it anymore, From now on, you will see VR systems at 90 degrees to 110 degrees, like this one. Pancake lenses, the Pico G3. That's the Pico G3 also. That's the new Panasonic lenses. This is a Copin. Lucid is a little different. And then this morning, that was this morning actually, that's the new Vive concept, VR headset. See, I included this morning. I included a slide. That was actually published this morning. So, you really have state of the art today. It happened this morning, and you get it this afternoon. It was a class. And this is a concept also. So I'm pretty sure there's a pancake lens, a plastic pancake lens in there. This is very interesting. There's a company called FireTech. It's a spin-off of Lockheed Martin. You can check it out. This is very interesting. So it's a video see-through light field system. So what do they have? Well, they have micro lenses that capture the light field on individual detectors here. Individual detectors in a honeycomb. So in this honeycomb, you have multiple micro lenses here, and they capture a light field. Then on the other side, you have an array, the same array of micro lenses with an OLED display that provide the same light field, but in between you superimpose digital information. So that's a small form factor with a 200-degree field of view, light field, and this is an optical architecture that actually works. So it's from their website, so you can actually check it out. Now they don't talk how they process the information. That's going to be a real tough one. But the optical system is there. The optical system of the future. Small form factor, 200 degrees field of view, light field, very low form factor. I think that's the best optical architecture, provided that there would be a chip that could actually process that amount of rendering. Vestibular comfort. Now, of course, it has to be untethered. The device has to be untethered. Cannot be tethered to a PC. Cannot really be tethered to a pod like on Magic Leap, because it's really not easy to go around, especially in an enterprise surrounding. Pivoting visor is very important. If you have a problem, for example, a surgeon that has a problem, just pivot the visor up. This is another example of. This is actually an example that I show at universities. This is at Photonics Europe 2 years ago. We had this optical design challenge that we. I think there are a few students from Honghua students, who Yeah, actually got awards also at the Optical Design Challenge as part of AR, VR, MR conference. So this is a student that that won a challenge, and he actually decided to open his company and hire people, get some money, and develop his own mixed reality video see-through with this 2 millisecond lag in between. So that was unveiled last 2 weeks ago. So this is a video see-through MR system which uses multipath lenses. So these are catadioptric multipath lenses which use 4 different displays per eye. So he was able to reduce the distance between the display and the lens in order to push the center of gravity closer to the center of gravity of the head. And of course he uses the XR2 chip also, which was just unveiled by Qualcomm to power the entire headset. So here you see the catadioptric lenses, the light folding optics. So I'd love to see more students, after winning an Optical Design Challenge, doing this and creating their own startup. And then the guy is 25 years old. Okay. So visual comfort. Remember, the first one was wearable comfort, then vestibular comfort, and visual comfort. And how long do I still have, John? How long do I still have? Okay, so can you still stay with me 5 minutes? Yeah, 5-10 minutes? It's okay? Good. Visual comfort, non-conflicting 3D cues. Well, Professor Honghua can talk about this much better than me, but I'm going to do my best. Solving for versions accommodation conflict. Well, most of the devices today are based on stereo display. This is a 200-year-old concept. This is actually much better than HoloLens V2 because you can change the focus. You can change the distance between the lenses and the display, which we cannot do in HoloLens. So this is the versions accommodation conflict in diopters as a function of the image. If the focus is at 2 meters, depending on the optometrist you're talking to, a quarter diopter versions accommodation conflict is permissible. So you can actually present with stereo disparity your image from 1.3 meters to 4 meters. If you talk to another optometrist, he might actually say half a diopter. Versions accommodation conflict is permissible, so you can go from infinity to 1 meter. But what happens here in the near field? Well, you get this versions accommodation conflict, which is basically vision discomfort. Now you can play tricks like multifocus, such as Avegant, or varifocal, such as the latest Oculus. They have switchable LC lenses. This is an example on how it's used. But you can also use integral imaging. This is Gabriel Lippmann, who invented integral imaging, light field imaging, or holographic display. Now it's really, which one will win, light field or digital holographic display? I don't know, but what I know is that there are some companies that already unveil digital holographic head-mounted displays, such as VividQ 2 weeks ago, and other companies, such as Serial. These are actually based on MEM scanners, light field display. This is a Chinese company that aims at providing a field of view of 60 degrees, light field display, dual-depth linear mixed, just like Magic Leap, at 126 grams. So good luck. We'll see if this goes anywhere. So to conclude, display is not everything. If you have a good display, but your sensors are not up to the task, the mixed reality experience is not good. So you have to have a very good sensor fusion. Sensor fusion means you get all the data from all the sensors. The sensors could be 6 degree of freedom head tracking, 3 degrees from the cameras that look on the side, and 3 degrees of freedom from the IMU. Then time of flight spatial mapping, SLAM, simultaneous location and mapping, GGV, which stands for gesture, gaze, and voice, and why not EEG and EOG brain sensing. This is an example of the spatial mapping in HoloLens V2. Now, of course, you want to do spatial mapping, but you want to recognize also what you scan, a table as a table or a chair as a chair. So we included some artificial intelligence in the version 2 in the scanner. So you scan your reality on which you want to superimpose digital information, but you want to recognize what you scan. Universal eye tracking, very, very important. So we use here a glint-based eye tracker, not only for eye tracking, but gaze tracking, pupil tracking, versus tracking, stress tracking, and emotion tracking. Fully articulated hand tracking, which is actually done by the time of flight sensor. So we have 2 operation modes. In the time of flight sensor, the far to scan your reality, and the close up to scan your hands and your arms for gesture sensing. And then, of course, EEG. These are some tests that we did. So EOG, obviously, in the front, for electro-oculogram scanning. So you can actually get a sense of. You can actually have an eye tracker without the optical sensor. You just track the waves. The electrical signals on top of your nose, and you can actually sense where your eyes are looking. And then in the back, of course, EEG sensing. This is a sensor fusion chip. We call it the holographic processing unit. It's a 28 nanometer chip. Actually, in V2, it's a 7 nanometer chip. Okay. Of course, with all this, this is a IEEE article that I really like. With all this, with the best display, let's say you have the best display, optical foveation, large field of view, you have the best sensors, you still don't have the accuracy that you might have with your natural vision, just because of the lack of focus accommodation in your system. If you have a system that has a fixed focus, you will always have registration errors between your holograms and your hands. This is just because because of the vergence accommodation conflict mitigation. And this was actually pointed out by surgeons. So if you cut something that is only 2 millimeters away from where you should cut, you can actually lose a life. This is really problematic. Social comfort, that's the last one. It's very, very, very fast. Nobody wants to look like a bug eye, in social environments. So a lot of companies like Huawei or Amazon or Google or Bose think that's the first step into mixed reality, not really mixed reality, but smart glasses, is audio smart glasses, audio augmentation rather than visual augmentation. And I think they're right, because anybody who tried to sell augmented visual information, such as Google Glass or Intel or North or any of these companies, will fail today because there is no consumer market today. There is an enterprise market, but no consumer market. But interestingly, smart glasses based on audio augmentation sell very well. Smart glasses based on visual augmentation do not sell well today. This is something to remember. The last thing about social comfort is eye contact. This is something that we don't have in HoloLens 1 and HoloLens 2 because the gratings diffract light in both directions. So you have light coming out on the wrong direction. You can't even have eye contact. So we're working on rejection notch filters that filter out the laser light without really impacting the color of the see-through to get rid of that image. This is especially true, when you're in a social surrounding and people look at your eyes. When I look at somebody, I always look in the eyes. You never look at somewhere else. It's just the eyes. And if you don't see the eyes, you don't have the social contact. So any mixed reality system, smart glasses that will not allow you to look in the eyes of the wearer is going to be a failure in the consumer market. This is not a consumer product. Now, of course, also in the battlefield for the army, you look like a beacon, in the battlefield. So, it's not a real good solution either. So what about getting closer to the eye? Do I still have 5 minutes? You can go closer to the eye. VR headset, AR, smart glasses, smart contact lens, smart intraocular lens, smart retinal implant, and why not visual cortex? So you don't even need to go through optics class anymore. You can go directly to neural tech. So a lot of companies are actually looking into smart contact lenses as sensors and smart contact lenses as displays. One of the old, if this is actually interesting because these are figures of my book. So if you want to have the details, buy my book, or you ask John, he's gonna, or Hong, she's gonna have the slides for you to review afterwards. So we went closer to the eye. What about getting further away from the eye? Parallel realities. Well, this is the future, I think. You're going to be walking down the street and you look at the window and you see something real through the window, but then you have a projector and an incoupler that would actually project and augment digital information on top of your reality, and an infrared flood sensor that will actually scan your face and recognize you. Oh, hi, you're blah, blah, blah. And obviously, that lady would be with her husband here, and she would get only information for her, not for her husband, who is only 1 foot away. This is parallel realities. And this is basically at a shop and say, hey, we have a special on that diamond. Maybe you should tell your husband that, without actually the window showing this to the husband who's only 1 foot away, because the window recognizes the face and also has a gaze tracker here because the camera is right here. So the field is trapped by TIR and goes down here. And of course also solar cell applications, but I'm not going to enter into details here. So these are smart window applications for tomorrow for parallel realities. And this of course requires the industry to go from a wafer scale to panel scale. So this is in conclusion. I have a few words about the SPIE AR, VR, MR event that happened 2 weeks ago. I'm going to go quickly through it. What was interesting is Applied Materials CTO came and said, we want to help build up the global mixed reality hardware ecosystem so that mixed reality companies like Microsoft and others can focus on mixed reality cloud. That's the only interesting thing in mixed reality today for most of the companies that are developing mixed reality headsets. It's to sell mixed reality cloud services. So a lot of companies introduced new waveguide concepts, such as Wave Optic, Dispelix, AGC, which is Zai Glass, and Corning. Wave Optic partnered with Shot Glass to make new high index waveguide gratings. Bosch also introduced a new laser scanner, very small laser scanner, but I think they're actually targeting the enterprise sector, which is very smart. North introduced the V2, version 2, and TU's Zeiss, who knows one or two things about optics, showcased their larger field of view curved waveguide combiner. So why curved waveguide? Nobody else can do a curved waveguide because they only have one exit pupil. If you have one exit pupil, you can curve the waveguide. If you replicate your pupil, such as what we do, what Magic Leap does, what Wave Optic does, you cannot curve the waveguide. And this, of course, I showed already. And Will came up with a new bird bath design. And then micro LEDs, of course. Very, very interesting. Plessy is one company to watch for. And then Mojo, a company in the Silicon Valley, which has a 1 micron pixel pitch ILEDs that they put on a contact lens with an optical system that projects the image at infinity. So when I told you that people are actually working on contact lens displays, this is true. This is actually, they got nearly $100 million, to work for, mostly from Google. And it was really interesting to have their CEO here. Vision technology, the Prism Awards actually went to, in vision technology, to a waveguide grating company, Wave Optics in the UK, that shows how much waves this technology is actually producing in the field of AR. So that's their device. Okay, conclusion. I'm at the conclusion. What is the state of the art in MR hardware today? Well, and this should be blue, of course. The projector decided to make it red. We only touched the tip of the iceberg. There's still a long way to go to provide full comforts to mixed reality headset users in all 4 declinations. Remember, we started with wearable, vestibular, visual, and social. But stay tuned, this will happen way faster than you may imagine. That's exactly what happened 30 years ago, 40 years ago. Most of you were not even born. The industry wanted to push the optical data storage technology to the consumer, but had 2 big hurdles. Nano imprint lithography to make the CDs, and sell this for $5. Now, 3 lasers, 3 different detectors, active autofocus, everything aligned at arc seconds, hundreds of glass optical elements aligned, and all this $5. Now, of course, that was possible not because one company wanted to do it, but because multiple companies joined efforts to create this ecosystem, just exactly how you see it today. What happened, for example, two weeks ago, when glass manufacturer combined with nanolithography companies, with plate processing companies such as Applied Materials, to provide to the mixed reality developers an industrial ecosystem that will allow them to reduce the costs of these very complex waveguide gratings. That's exactly what happened 40 years ago. And the companies were not Facebook, Google, Microsoft, Intel, and Amazon, but these companies were Sony, Panasonic, and Philips. The largest companies in consumer at that time came together. Still were competitors and remained competitors, but came together to provide to the world these two technologies. And then, of course, each of them made a lot of money by the content, but they had to provide a hardware at lower cost. That's exactly what is happening today in the AR and MR industry. Yeah, and if you want to know more, you can actually ask Honghua the slides, or you can just buy my book. Thank you.